We are going to start our program right now. So good morning, good afternoon, and good evening to our participants today. Dear colleagues from academia, industry, and research organizations from home and abroad, ladies and gentlemen, greetings from the Department of Chemical Engineering, Bangladesh University of Engineering and Technology. I'm Saida Sultana Razia, head of the department, and I have my colleague, Dr. Naser Sanjida with me. We too are going to host this online program today. We are pleased to invite you all to the webinar on sustainability in the water, energy, food, environment nexus, the role of chemical engineers, by the third M.A. Naser Chair, Professor Rafiqul Gani. M.A. Naser Chair was initiated and established by the BUET Chemical Engineering Alumni Association at the Department of Chemical Engineering, BUET, in recognition of the contribution made by Professor M.A. Naser, pioneer in chemical engineering education in Bangladesh. And this is the first webinar of the series of webinars to be presented by Professor Gani in next few months. Before we start the webinar, I would like to briefly introduce our speaker today. Dr. Rafiqul Gani is the co-founder and CEO of a Thailand-based company, PSE for Speed, that provides engineering solutions globally to industrial clients. Dr. Rafiqul Gani is a former professor of systems design at the Department of Chemical and Biochemical Engineering at the Technical University of Denmark, and the former head and co-founder of the Computer-Aided Process Engineering Center in the same university. He has published more than 500 peer-reviewed journals, proceedings articles, plus book chapters, and delivered over 360 lectures, seminars, plenary and keynote lectures at international conferences, institutions, and companies all over the world. He was awarded the AICHE Computer in Chemical Engineering 2015 award in November 2015, and the European Federation Jacques Villomar Medal in 2019. He is also a distinguished professor at Zhejiang University and Tsinghua University in China and Texas A&M University in US. His current research interests continue with the development and application of computer-aided method and tools for modeling, property estimation, process product synthesis and design, process tools integration, with emphasis on energy sustainability and application of a system approach. Dr. Gani received his BSc in Chemical Engineering from Bangladesh University of Engineering and Technology and obtained his MSc and PhD in Chemical Engineering from Imperial College London. It is an honor for us to have him with us today. Without further delay, I would like to invite Professor Gani to start his presentation. Professor Gani.
Thank you very much, Dr. Razia. Can everybody hear me and see my screen?
We can we
Yes.
hear him?
Yeah.
Yes. Okay. So I would like to start by thanking the organizers, Professor Razia and Professor Sanjida, for arranging this webinar. And also wherever you are joining this webinar, thank you for your participation. As it was mentioned, I'm going to talk about the role of chemical engineers with respect to sustainability in the water, energy, food, environment nexus. Let me start by making the reference point for my presentation. On this planet Earth, we, the humans, are the master. There's no doubt about it. But in order to stay there, what should we do? And what we can see is that a lot of our activities are involved with water, energy, food, and they all impact the environment on Earth. However, our actions need to be also sustainable. So what I'm going to talk about is I will highlight the relations of energy, water, food with respect to environment, not all the interactions, just with respect to environmental solutions that can be obtained. So let's look at first the problem. If we look at the blue curve, that is the prediction of the global increase in population or world population growth. It says this was a few years ago that the population would increase to between 10 to 11 billion. I think the latest predictions have readjusted the increase and saying now that it will be between 9 and 10 billion. So if the population is going to be between 9 and 10 billion, what is going to be the demand? We can see that according to many experts, the global GDP would be increasing 6 to 7 times. That will require increased production capacity for commodities like steel, chemicals, wood, etc. These will require increased energy demand, increased electricity demand, increased water demand, and all of these will contribute to the emission of greenhouse gases. With respect to specific data, the food demand, because the population is going to increase, will increase. The energy consumption will increase. The global water consumption will increase. And all of these will increase the CO2 emission. You can get a copy of this, my presentation, so if they're too small to see, you will be able to read them afterwards. So what we can see is that just like the current problem of the virus, all the number of effects per day is increasing and we have to do something about it. But what is the effect of this? The effect of this is that the temperature on Earth, the average temperature is increasing. According to the agreement that was signed some years ago by all the countries, the increase until 2050 would be limited to 2 degrees. The current situation is not very good because already we are at about 1.4 degrees. So unless we do something urgently, we are going to cross that constraint that was agreed by everybody. But what does this mean, this increase of temperature? These are all data, not predictions, just raw data collected by different organizations. And the next pictures are real pictures, not manipulated pictures. We see that regions where the temperature can be very high, we are getting unusual weather patterns that causes cyclones, storms and things. And in certain regions, like in the poles, the polar bear does not have a home or is getting threatened. So what this means is that we need to take urgent action. We need to slow down the global warming. We need to reduce the water-land contamination. We need to stop the forestry destruction. We need to recover and reuse resources and many more. The question is how? And if you're interested in this, then the rest of the presentation, you can follow and I will show or discuss how as chemical engineers we can contribute to this. So now I will talk about briefly the problem and the analysis. So from a sustainability point of view, we can see again the human progress. If you follow the green curve, we need to sustain our progress, which means that at different times with our progress, we had to move from one technology to another that helped us to sustain our progress. So if we follow the red curve, that technology was becoming redundant, and before it became redundant, we had to find another technology that could allow us to sustain our progress. So sustainability, in a sense, is the ability to sustain the progress, or the ability to absorb the changes. So very simply, it's ability to sustain or the capacity to endure the changes. But whatever we do, whatever technology we develop, it also has a constraint. And this was actually based on a report from the United Nations in 1989, which says that development that meets the needs and aspirations of the present without compromising the ability of future generations to meet their own needs. So we should not just develop technologies, we also have to think of, is that sustainable with respect to this? And what I would say is that if one looks at all the developments that are going on, very few or many of them do not satisfy that. And if you want some examples, you can ask me at the end of the lecture and I will give you examples. So this is something that is serious because it is there, but why aren't people following it? More recently, United Nations again have developed this list of 17 Sustainable Development Goals. And if one looks at them, no poverty, no zero hunger, good health and well-being, quality education, all of these. These are very good. All the nations, member nations have agreed to it. And what I would say is that if this is achieved, then it will be heaven on earth. But let us see from a more practical point of view what can be achieved. And also from a chemical engineering point of view, we are not going to directly achieve all these goals, but at least if some of them can be achieved directly, it's very good. I will show this from another point of view, which is the climate risks against the Earth's capacity. As with the current pandemic, one can see that if we have business as usual and do nothing about it, actually we will come to a stage of no return, because we are going to go way above the Earth's capacity to absorb all the changes, and it will be, of course, not very good. Actually, we are still below the Earth's capacity, so there is still time to take action. What we need to do is to flatten the curve, just like in the pandemic, so that we do not go above the Earth's capacity. And so, if the objective is to flatten the curve, what can chemical engineering provide to help that? That means we can, as chemical engineering, we can provide the means to find ways to flatten the curve. And I will elaborate on this more. So let's see, first of all, some targets for improvement, because if we want to flatten the curve, we need to see where we can target as chemical engineers to help the problem. I've divided this just to give the concept 3 columns. The first column are commodities, that is the processes that produce commodity, chemicals, cement, steel, all kinds of production in bulk amount. The next one is pharma bio, and the next one is food and household. What we see is that the key to success with the commodities is cost, is economics. In pharma bio is the speed of developing the product and bringing it to market, and the food household is the function. Does it perform what it is supposed to do? The basis In the first case is unit operation, chemistry, microstructure, but let's just concentrate on the unit operation. And then in terms of the problem comes the energy, in the sense that these processes are energy intensive. And if it is energy intensive, the waste is CO2 and byproducts, because they will affect the environment. If we take the pharma bio, they are usually not energy intensive, but on the other hand, they're water intensive. And so a lot of water has to be thrown out. But the other problem with this kind of industry is that there is a lot of material waste. And finally, the one with food household is interesting compared to the other two, that water, which is also used as a process fluid, and energy could be used, could be intensive, like the farming of cattle for beef is very energy intensive. The other thing is also that water is part of the product, whereas water is not part of the product in the commodity and pharma bio. The fact that the pharma bio has a lot of waste as material, that is because of the atom efficiency. And this means that all the atoms that go in as raw material, a small percentage of it go into the product and a large percentage is waste. That is not the same for the commodity chemicals. So what we can see is that there is already indications of where we can target and what we can improve. However, based on the current state of the art, we need significant improvements, not small improvements. And so the unit operations that we are working with, or the chemistry that we are working with, we need new chemistry, new unit operations. We need to discover new microstructures so we can get significantly improvements in process and products. And of course, chemical engineers can contribute quite a lot to that. Let me now explain a multi-layered view of chemical engineering. At the core, what we say is that chemical engineers or chemical engineering is all about converting resources to products that the society needs. And a process is a typical process that the chemical engineers would design based on the fundamental principles that they would learn, like thermodynamics, reactions, separations, transport phenomena, and so on. And then based on these fundamental principles, they will design, build, control, operate. But the resources conversion is not 100% converted, so there will be also wastes. And that's the core. Every chemical engineer would be expected to know this, but is that enough? That is not really enough, because we are not talking about the availability of the resources. We are not talking about the demand of the resources. And we are not talking about if the products are improved, if the waste can be reduced. So if we take all of this into account, we will get a sustainable technology. To do this, to get the sustainable technology, we need more advanced fundamental principles. That's where we need to combine the science and engineering. But is that enough? And that's why the multi-layered, the final layer is that we want to get the optimal products, the lowest waste, the controlled environmental impact, and so on. In terms of resources, we need to look at location, we need to look at type, demand, availability, recovery, and so on. The final result would be a sustained society, sustainable development in terms of industry, institutions like BUET and all this. But in order to do this, we need integration of ideas, disciplines, data, and so on. And I think chemical engineering is already built in such a way that we can glue all these disciplines and ideas together to find a solution. If you're interested more in this idea of view of chemical engineering, please look at the publication which came out this year, early this year, in Chemical Engineering Research and Design. So what would be the contribution of chemical engineering? Problem definition. We can identify the system, which can be process, which can be product, versus their impacts, which resources to use, and so on. We can evaluate alternatives. Are those alternatives sustainable? Which one to select? Development of methods and tools. We need to, in order to do the evaluation of sustainability, we need to calculate the measures of sustainability. We need to do the sustainable process design, the modeling, the database, all of these. And finally, mitigation or management. In addition to management of CO2 emission, water, energy, so on, I would say that we also have the responsibility to educate and train the general public on the problems that we are facing, how to solve them. And at the same time, if we cannot make the decisions, we need to influence the decision makers, which is very, very important. Based on that, now let's look at the measures of sustainability. Both IChemE and AICHA around 2002 published a list of 49 metrics that could be used to calculate them in economic and society. How much energy was used or how much water was wasted. Those are the measures in terms of environment. In economics, it's clear: profit, tax, value of the product. The societal is more difficult to measure. As a result of the product or process, how many people got jobs, were their schools built, were their hospitals built, how the quality of life improved. These are social. So these are numbers that can be calculated with respect to the impact. If they're positive, it is good. If they're negative, it is bad. In terms of the material land usage, if the value is close to 1, is good, and we should try to keep it as low as possible. But you can see that if the value is 0, then there is no process or product. So it has to be usually greater than 0, mostly greater than 1, but depends on how bigger the value is. With respect to profit, of course, the higher it is than 1, it is good. So all of these, then if we can calculate very quickly, we can identify where is the problem and what can be done about it. Note that sustainability is is not an absolute value, it's a reference value. That means we need a reference, and compared to the reference, we see how the new alternative is. Okay, with these, now we can see how do we actually calculate it. That is typical engineering or chemical engineering. We have a system with a boundary, and for that system, we put all the input. It's not just the material and energy input. We can say data input, we can say money input, people input, all kinds of input, as well as all kinds of output. Because of the knowledge we put in, we get models Because of the material we put in, we get product. Because of the energy we put in, we get heating power. Because of the people and money we put in, we get jobs, and so on. So we need to have all the data of what is the input, what is the output, as well as what are the wastes. If we have all this data, we can calculate what we said, 49 sustainability matrix. S is the sustainability metric, J is the indicator from 1 to 49. If we know the input-output relationship, we can calculate all of them. In some cases, the input may be 0. In some cases, the output may be 0. In some cases, we will use input minus output. In some cases, we will use a ratio. So this will give us the metric compared to a reference. And if you have heard also of carbon footprints and all of these are also calculated based on the available information. Carbon footprint, ecological footprint, hydrogen footprint, nitrogen footprint, water footprint, all kinds of footprints are being proposed. But the most important are the carbon footprint and the ecological footprint. So if we know all of these things, then we can make decisions on what to do. So now let's say that we have several alternatives and we need to select one. And I show you on the plot on the left, on the y-axis is the environmental impact, and on the x-axis is the profit, and the different dots are the different alternatives. The bottom left-hand square is low impact, low profit, and the one above is high impact, low profit. The dark blue is high impact, high profit, and the one below, the right-hand side, bottom right-hand side, is the high profit, low impact. And then we can see that from the sustainable development goals, if we want to reach the one below, the green, this should be obviously the solutions to the extreme right on the bottom square. And the solution that we don't want are the ones in the top right. So to get the solutions on the bottom right, as I show you here, these ones are non-trade-off solutions. These are more sustainable. They decrease the environmental impact, they decrease the energy consumption, this is safer production, more profit, everything good. If we forget about the environment and just make more profit, we get the solution above. So there's a clear choice what we want to do. Also, people say that if we want to make a better environmental solution, we have to pay for it. What I would say is that that is not correct, and we can show it here. And I think we should always be looking for these kind of solutions, and should force people to look for these non-trade-off solutions. So let us take three variables: cost, carbon footprint, and waste to represent the economics, the environment, and the resources. Obviously, if we reduce the cost, reduce the carbon footprint, reduce the waste, we will improve the profit, we will improve the environmental health, we will improve the resources. How can we do it? By decreasing the energy consumption, by decreasing the water consumption. How do we decrease the water consumption and energy consumption? If we make the process more efficient, if we reduce the demand, better design. And then we can show it like this spider plot. The boundary is our reference. Any solution that is within the boundary is a better, more sustainable solution. Anything that goes out at any of the vertex, then it is a trade-off solution. And we should be looking for the non-trade-off solution. If people say that we have to pay for the environment, environmental improvement, then they're not looking for all the solutions, or they have missed, because clearly it is possible to find non-trade-off, truly more sustainable solutions. So this is our target. This is what we want to achieve. Now we go to the third step or part where we discuss the important issues. Again, typical engineering problem. Now the system is a process. The blue variables are all the input variables. The green variables are all the output variables that we will calculate. The red variables are decision variables. We have to decide which raw material to use, which utilities to use, which product to make, how many processing steps. So what we can say is that as engineers, we have to make decisions, and based on those decisions, we will calculate things. And those calculate things that we will calculate will impact the environment and our future. So it is important that we know how to make the decisions, we know how to interpret the results. Okay, how do we make the decisions? We need to understand the relationship between the product and the process. As we said before, to sustain ourselves on planet Earth, we need to continuously improve the products that we are making from the resources that are on Earth. If you look at the current state of the art, we are converting we are making useful product from resources that we have, but we need to define the product to make. We need to identify the raw material to use. We need to identify the process that can manufacture the product in a sustainable manner. However, at this moment, this is not very good, because our useful product, or let's say efficiency, is only 25% compared to what is needed. That means in order to have a sustainability of resources to product and services and environmental impact and so on, the efficiency of conversion needs to be more than 40%. And we are currently at less than 20%. And that is a situation that, as we said, business as usual, we will cross the Earth's capacity to handle the changes. So significant improvement is necessary. But here also, I would like to point out the issue between prevention and cure. What I say prevention is that prevention can be done through technical solution. For example, we are designing a process. If we choose the right chemicals, the right solvents, the right energy, we are not going to have a problem. If we choose wrong one, we may have contamination of water. And if there is contamination of water, then the pollution has already occurred and the problem has to be cured. And the curing of the problem is more a technical, social, economic issues, but the prevention is just a technical issue. So if we can prevent the problem, we don't need the cure. The same goes with the design efficiency. If the process is working fine, we don't need to improve the efficiency, but we see that the efficiency is not good and can be improved significantly. So what we see is that more and more we are involved with the curing of the problem, but we could have avoided this curing of the problem by preventing it in the first place. This is also very similar to the current situation. The pandemic has already occurred, and curing that problem is much more difficult if we had taken the steps to prevent it. Okay, so now we can see that we need to choose the right raw material, the right product, the right process, and make the calculations. So the tree that you see on the left, at different levels, there are different kind of products, you can say, in terms of chemicals. And in order to go from one level to another, we need a process. So at the bottom is the raw materials, petroleum, natural gas, biomass, phosphate, and so on. And then some basic chemicals and intermediate chemicals all the way to the top, which could be some fancy products. And so for each of them, we need to find out which product we need, which raw material we need, what kind of process we need, and so on. If you want to learn more about it, it's given in this paper. So I will just skip that and point out that these are the questions we need to answer. What, why, when, and how. How is related to the process. What, why, when is related to the product, the raw material, and so on. In the tree is shown just a few of the raw materials that are used to convert. Here you can see a bigger, with the earth, a bigger collection of all the resources, or not all, many of the resources that are available on earth. And then one could question, why do we use fossil fuel and not solar energy? Or why do we use coal and not solar energy? Which minerals do we use? Which metals do we use? And so on. So we will discuss this also, but there is a clear decision that needs to be made, which is the best decision related to what to make, why to make, and when to make, and how to make. Okay, let's look at more detail now. Let's say that our core topic of chemical engineering is to convert resources to product. I'm just showing the core level, but actually it should cover all three. And we can decide on the raw material and the products and the process through the tree. So the first thing is that we want to convert resources to products. We need to select a processing route. Once we have done that, in order to produce the product from the resources, we need to use energy, water, solvents, and others. So we need to design, simulate, operate the process. As a result of doing this, we are going to impact the environment because we are using energy, we are using solvent, we are using water. So what are those impacts? We need to calculate them. And based on those calculations, we need to set targets that if this value is greater than this, it is not acceptable. These values must be lower than this. And then based on those targets, we need to change the design so that we can find alternative that will match the targets. If the targets are matched, we have a more sustainable solution. So these are then the basic functions, not at just the core level, at all three levels. So now let's, based on this as the background, let us look at some examples of sustainable alternative developments. The first one I will select is with respect to energy. And this is a report, a figure from a report by the International Energy Agency in 2015, where they pointed out that the industry, in order to improve their efficiency, actually in order to match the target of 2-degree increase in temperature on Earth by 2050, these are the actions that needed to be taken. And they pointed out that for industry, the energy efficiency has to be increased significantly. That is very good because that's what chemical engineering is going to do, is going to improve the industry energy efficiency. Note here that the dark blue in this case is CCS, carbon capture sequestration. Does that, my question would be, does that satisfy the requirement of United Nations from 1989 that we must not do anything now that will affect our future generation? It may not affect our immediate future generation, but some future generation will be affected because all this will have to come out. So I'm not sure that I would accept CCS should be there. Okay, now one of the ways to achieve this significant improvement in energy efficiency has been pointed out one technology, which is process intensification, that it can actually improve significantly the energy or the material usage. So if we say that the objective of process intensification is sustainable circular economy, not that it is not circular economy, because circular economy cannot satisfy the laws of thermodynamics. Maybe the money can satisfy the circular economy, but not the material, not the energy. So it has to be sustainable circular economy. So how do we achieve the improvements? Any of those improvements, higher productivity, multitasking, increased efficiency, safe, reliable, one or combination of all of these will help us to get the improvement we need in terms of sustainable circular economy. How do we get it? These are classical chemical engineering, not only at the core, but at the higher levels also, reaction path, species allocation, heat power management, rate size mechanism, tasks, scale up, scale down. It's not just minimizing the size, but also increasing the size, controllability, operability, and so on. And the result of this is a new unit operation, a totally new process, totally new network of processes. All of these will significantly improve on the current state of the art. A note here is that we are talking about new equipment. So we have to forget the unit operation. Excuse me. So PI has been identified as being alternatives that can provide significantly better solutions. Here, I would like to also highlight one of Buet Chemical Engineering graduates, Farooq Hassan. He is now associate professor at Texas A&M University, and he's becoming a world expert on process intensification. So very good work. So just to show you an example, what you see on the left-hand side are two flow sheets of chemical processes. We have a reactor followed by separation, and these are vapor-liquid separation. In principle, any processes with a reactor followed by separations can be converted into a reactive distillation. And this is a PI solution that is guaranteed to give the same product as the processes with significant improvement in reduction in energy, material, and so on. So if this was such a magic solution, why are industry not using? Only few examples can be seen, because they are still not sure that this is really, it will work. Too good to be true, maybe. But that's where we come in again. We have to influence the decision makers to convince them that this is really the solution. One could also ask, okay, if this was possible, how many chemical processes can be replaced with a reactive distillation? I would answer that by these questions. You see all the questions with respect to reaction, mixture, separation, other. If all the answers to these questions is yes, then that chemical process can be converted into a reactive distillation. And all we have to do is to calculate how many stages we need for the reaction, how many stages we need separation below the reaction, above the reaction, what would be the condenser, what would be the reactor, the reboiler. With that design, only we will replace an entire chemical process with that. Now, can you imagine the thousands of chemical processes that could be converted to this? That would make a significant improvement if we can convince the decision makers that this is a good idea. And to do that, we need more work. And for example, work to prove that the design process will actually work, is controllable, is operable, and requires less energy. I'm happy to report also that we have been collaborating with the PAC group at the faculty at the BUET Chemical Engineering Department, and it's also with international partners from Korea, China, Thailand, Denmark. And now we can show clearly that reactive distillation can be designed in such a way that it would be best to operate, best to control, much better than the original. So improvement can be made. Another one is hybrid operations. And again, you see chemical processes. The highlighted unit operations are actually distillation columns. Why are we targeting distillation columns? Because they use a lot of energy. And if we can reduce those energy, we will reduce the total carbon footprint. And it turns out that distillation is very efficient up to a certain purity. So if we want to go to 99% purity product, up to 90 or 95%, distillation could be very good. Nothing to beat it. But for the last small amount of purity, it uses 80% of the energy, total energy. And that cannot be very good. So can we replace this final separation with something else that does not require so much energy? And the solution is a hybrid. We operate the same distillation column, no changes. We just reduce the reflux. We get a less pure product, but it uses only 10 to 20% of the original energy. And then we put a membrane, if we can find a membrane material, to do the final separation by removing the small percentage of the impurity that is there. It's not going to remove the high purity product, it will remove the low impurities. And by removing the impurities, we get the more pure product. This requires hardly any energy, and we can find many examples of currently operating distillation columns that can be replaced with this hybrid with significant improvement in energy. We can also combine two distillation columns together, or three, into this kind of combinations, putting a membrane also where needed. So the rule: combine two types of techniques such that each operate at its highest efficiency, saving 10 to 50% of energy consumed by the single. There are at least 100,000 operating distillation columns on Earth. Opportunities are there to make an impact. So again, actually here we have made more progress. Some companies are beginning to listen and would like to find more details on how to add the membrane unit or other adsorption or other techniques. Another one is integrated network. Here we have the manufacturing process. It's designed to minimize everything. CO2 emission is perfect, but where is the actual boundary? Is the boundary just the process, or the boundary includes the power plant which will provide the power? And then should the power plant use the fossil fuel or other sources of energy like solar, wind, or nuclear? If we combine all of this together and solve a bigger problem, we could actually find solutions that will be zero CO2 emission. We also have to see here is that there are energy demanding processes like the manufacturing process and the energy supplying technologies like the power plant. So we have to combine them in such a way that we have a zero emission solution. If we do not do that, the solutions will be superficial and not very useful. And so what we need is new innovative solutions that are significantly better, and we can reduce the energy demand to the process to reduce the CO2 emission. At the same time, we are not going to use fossil fuel for the power plant, but we'll use solar, wind, or nuclear. And so we are not going to get the CO2 emission. And whatever CO2 is emitted, we will capture and use it in the process to manufacture something else. Is that possible? Let's look at this kind of problem formulation. So here is the process. We look at all combinations of the process network to find the best process, assuming that whatever water we need is available, whatever electricity we need is energy we need is available, and we will minimize the waste of water and energy. But we are assuming that all the energy we need is available, all water we need is available. That's the typical problem that we solve. But now we put availability limit. On any type of energy we use, we say so much is available. Then our solution will be different. We can tackle that solution, but then we could say how we will convert the energy source to the energy supply that we need. We will also optimize that. So what would be the power plant? What would be the solar energy conversion, oil energy conversion, and so on. And whatever CO2 is generated, we will use it within the process. Similarly, with the water, we will recycle the water so that the fresh water would be reduced. And this would be the solution that we are looking for. Can it be solved? Sounds very difficult, but actually just got information yesterday night that our paper giving an example of this based in China has been accepted. And in this paper, we give the design of a process, we give the design of the power plant, of the energy conversion, of the water conversion. All together, we show a zero environmental impact solution. So these are possible. Finally, the last example is not with respect to the process, but with respect to the product. And we call it chemical substitution. And the idea is that chemicals can cause problems if they go out, like in the case of automobile or agrochemicals or process solvents, paints, cosmetics. They can cause environmental hazard, they can cause human health hazard, they can cause problems of operation because of regulations within Europe, within USA. So we cannot just choose any chemical. If we find a chemical that is causing the problem, we have to replace it. So the steps would be identify the contaminant, identify the function that the contaminant was doing, find an alternative chemical that has all the good properties, but not the bad properties. Verify the function, confirm the improved sustainability. This is a problem that exists everywhere, and I'm sure there's a lot of problems like that in Bangladesh where this can be applied. So what could be the solution? So in order to develop the solution, we need to create a database of chemicals, all kinds of chemicals. Because the database will not have properties we need to develop models for properties. And then we need to develop a computer-aided kind of framework through which we can tell step by step what the calculation would be, including experiments that would be required. Here also, I'm happy to say that we are collaborating with the CPI safety group at Buet Chemical Engineering on developing additives database for chemical substitution. And the results are going to be presented at the AICHE annual meeting this year in San Francisco, most likely as online presentation. and then afterwards paper. So just to give you some number, the database, when we started with, we had about 12,000 compounds. Now we have managed to collect around 75,000 chemicals. For that, we have information. And wherever there is a gap in the information, we are developing models that will give us those information, missing information. And you can see that the models have been also improved significantly. If you look at the second lowest, that is the reference model, and all the others are the new models with significant improvements. So based on these examples, what is the perspectives and conclusions? What I would say, and again, I take it this statement from Adisa Azapajic, who is a sustainability expert in Europe, turning these challenges into opportunities. We have all these challenges. We have the opportunity to develop new technologies that will take care of this. So one thing we can highlight here is the resources on Earth is not uniformly distributed. We know that. Water, whether it is water, whether it is energy, whether it is minerals, they are not uniformly distributed. If we take the case of the energy, we have fossil fuel as one source, and we have also solar energy as one source. But we are using mainly fossil fuel because it is cheap. We have a technology that works, and we prefer to use that. But it is also causing all the global GHG, the greenhouse gas emissions, and global warming. We need to increase the use of resources like solar energy and others that are more expensive now, but that does not cause this problem. So maybe all the electricity should be produced with non-fossil fuels, and the fossil fuel that we use and the CO2 that we generate should be captured and used in other. Then we will have a zero CO2 emission solution. And we need to convince the decision makers on this. And this is just one example. We can find many other examples. Another example, I would say, find new and novel solutions to old problems. And these are actually what I've seen, that plastic waste is a big problem now. Everybody agrees. We have to reduce the use of plastic. We also have to find ways to convert the plastic. And actually, coconut leaf can make the straw. Should we use the plastic straw, or should we use this kind of straw? I don't drink anywhere, if somebody gives me a plastic straw. I use either the glass, or I sometimes carry my own straw. So we should not use the plastic straw. Same with packaging. Maybe we should take over the world again in jute, because why should we use plastic when jute is there? Similarly, water pollution. I think in Bangladesh, textile and cleaning, and even drug waste is a big problem. What can we do? Novel waste water techniques, treatment techniques can be used. And on the right, you can see one solution that was proposed recently. Why not, when we treat the water from the textile, why not kind of spray the water into a nozzle which is heated, and then the water will vaporize through the nozzle, and the solid material would come down as solid waste, as a powder, solid powder. And they showed some experiments, and it's working. And now they're going into production for that. Something like that can easily be done in Bangladesh also. I also put refrigerants. We need air conditioning, so we are using a lot of refrigeration, a lot of power. Can we optimize that? can we replace the R134A with something else? The metals, actually people do not talk about that much, but if you look at the periodic table and look at the red boxes that are there, zinc, arsenic, silver, and so on, these are supposed to last, or we are supposed to get not have any more unless they're recovered and recycled between 5 to 50 years. Red is that they will disappear between 5 to 50 years. Are we doing anything? We are concentrating on energy, on water, but we are not doing anything about these metals or rare earth metals. And just think of it, in the Western Europe, Japan, North America, there are 1.1 cars to the population. In countries like China, India, Bangladesh, it is between 0.2 to 0.4 cars to Bangladesh. What would happen if these countries decide to have not 1.1, but let's say 0.6 cars to population? There won't be enough metal to satisfy the whole world. So it is a big problem that at this moment people are not talking about. There is also iridium. Iridium is used on the mobile phone, and it's not going to last very long. Some estimates is that within the next 5 to 10 years, iridium is going to be finished. So unless it is recovered or another technology is found, we have a problem of sustainability. So finally, let's say what is the role of chemical engineers. And chemical engineering and related science and techniques must play a key role in meeting future societal needs, as well as, of course, all the things that we are supposed to do. So these are in addition. Promote research and development as a fundamental pillar and encourage technology development to achieve a planet able to sustain a growing population while improving quality of life. Facilitate global dissemination of chemical engineering technical knowledge and industrial best industry worldwide. Promote conservation and care of global resources, health, safety, conduct for chemical engineers worldwide, and to safeguard the public, as well as to influence the decision makers. Finally, with respect to the pandemic or disasters that can occur, prepare with methods and tools that can contribute to quick problem resolution. So contribute to achieve sustainable development. That is the end. The two last slides are some references that you can read if you're interested, and some views of sustainable development. Thank you very much. If you have any questions, I would be happy to answer.
Thank you very much, Professor Gani, for a wonderful presentation. So now we have time for a question and answer session. And I would request our participants, if you have any question, to raise your hands. And in our chat box, there is already some questions. I could read out
yes,
some of them. Yeah, some of them I can read out, and some of the question maybe the participant can ask directly. If someone raises hand, I think Dr. Nahi Sanjida will be following that. Okay, so I saw one question in the chat box from our Salek Sufis from joining from Australia. He said that what happens to huge coal reserve if world abundance coal power generation for limiting emissions? Can other fuel or renewable energy meeting the growing demand? And also, so why, and another question, so why CCS is not acceptable, you said. Yeah.
Okay. So let's start with CCS.
Okay.
CCS is capturing the CO2 and not considering what to do with CO2, we are putting it underground. But it is going to come out.
Yeah.
And if it is going to come out, then we are going to have even more CO2 than we originally had. So I cannot see how that can be a good solution. It is a temporary solution, I can agree, but it's not a solution that will last generations. That CO2 will ultimately come out, and then it will cause a bigger problem. With the coal, yes, we need to, at this moment, if we look at the amount of CO2 emission, coal, natural gas has the lowest, and natural gas, and then liquid fuel is higher than that, oil is higher than that, and coal is the largest. Yes, we do have abundant and it is cheap, but at the same time, it is causing bigger problems for the environment. And what I would say is that there are a lot of research going on in some countries that I know, especially, for example, in China, where they're looking at how to combine coal gasification with power generation, with chemical process and all of that. So together they can find a better solution than just using coal for power. So what I'm saying is that if coal should be used for power, it should be combined with other things so that the effect would be minimum. Otherwise, we are not going to keep the temperature increase to 2 degrees as everybody agreed by 2050.
Okay.
That was my answer.
Yeah. Okay. We have Dr. Farooq Hassan raised hand to ask a question. Dr. Farooq Hassan, Associate Professor from Texas A&M University. You can ask your question, Farooq.
Assalamu alaikum. Thank you so much for the floor. And Professor Gani, thank you so much. I really want to acknowledge that for the excellent and intriguing presentation. I always learn a lot from your presentations, but this was really visionary. I have two questions. The first question is related to the sustainable development, which really goes back to the increasing use of renewables. For example, we are already observing in the US, at least during this COVID situation, that there has been an increase in renewable contribution in the electricity sector. But my colleagues from petroleum engineering, they keep telling that we still need to use fossil fuels for the molecules that we need for the chemical industry. So what are your thoughts on that? That what kind of new feedstocks that we really need to focus on?
Yes,
from
I actually agree with that, because yes, we should use the renewable resources for power, electricity, and we should use the petroleum to make chemicals. Because, and then whatever CO2 we will generate, we will capture and we will also use it. So then we can actually find CO2 zero or even negative emission solution. This is the kind of solution I was also talking about with network within network within network, because our solution is located in a particular area in China where they have coal. So we have taken the coal, but we have said that we will use so much coal for which the CO2 that will be generated can be captured. And for the remaining power, that region has solar, a lot of sun, so we will use the solar power. And we are producing chemicals that are useful, and the water we are recycling, so it is almost like a self-sufficient. solution. So I would encourage that kind of research. And if the petroleum companies say, okay, we will make more useful chemicals with it, that is very good. And we can even suggest to them that if they combine CO2 with ethylene or methanol, they can make a lot of useful products. So they can increase the production of methanol rather than ethylene or some hydrocarbons. That would also contribute to the reduction of CO2 emission and the environmental impacts. So that's a very good question, and I hope you people in Texas are also going to do research in that area, because you have the solar power, you have the oil, you have the natural gas, you have the chemical plants, so, and probably also enough water. So combine all of them together into a super network that can be self-sufficient.
Yes, thank you. I think that's a great point. Texas could be a great test bed for regional level sustainability development.
You need to get rid of the president first.
Yes. Can I have another question? Do you have time for that?
Yeah, you have. You can go on. I mean.
Okay, so the other question is related to your work that you showed on the process intensification and the hybrid operations, which I think I believe really intriguing in a sense that traditionally chemical engineers like us take materials like catalysts and membranes or solvents from chemists and then use those, build chemical processes around those materials. But here what you're suggesting are these innovative designs that maybe material scientists like coming from a membrane background does not need to look for the end-to-end separation process, just focusing on the optimal optimal part of the membrane versus the distillation. So in that sense, are you suggesting an inverse way of complementing their research, that where their research should go towards guidance?
Yes, in two ways. Again, I mean, if people are also in Bangladesh, if people are doing studies in membrane, designing membranes, I would say focus on membranes that can be used. Because if I talk with membrane people, they cannot give me a membrane that will do the same separation that distillation does. The current membranes that are available, if we want to replace a distillation column, it will require a membrane unit which is more than 1 kilometer long. So that's not a practical solution.
Right.
So what we need is membranes with better permeability and selectivity. But until that happens, should we just continue with the distillation, or should we look for the short-term solution, which is combining the current membranes with the distillation? Because some of the current membranes can do a small separation very efficiently. So the hybrid can be a future also, but in the short term, the next 20 years, I don't see anybody coming up with a membrane that will replace a distillation column. But immediately, we can already replace a distillation column with a hybrid and immediately save between 10 to 50% of energy. So if we focus on, here is the separation, can we find a membrane that will do it? Instead of trying to find the magic membrane that will replace the whole distillation.
Okay. We have more questions coming out. We have one question from Chinmoy Boshak. He's joining us from Auburn University. Fourth industrial revolution, like how can chemical engineers contribute towards sustainability using big data? That's his question. Like, yeah. How can chemical engineers contribute towards sustainability using big data? That's what his question.
So big data, again, first we have to collect the data. We have to make sure that the data are consistent. After we have done all of that, then we can see with respect to forecasting, predicting the future, we can diagnose this is the problem according to the data, and then what could be the solution, better model. So better predictive model with the big data to find the interesting products that we need and the raw materials or whatever impact they will have, all of these. So yes, this is very important, but we need to use it in a way that gives us the solution of problems that we are interested in. We are not interested in some small minor problems that we can already solve. We are interested in problems that has no model at this moment, no theory at this moment. There is a lot of data, but we cannot organize the data in such a way to identify what are the indications, trends. So if we use big data analytics, machine learning, algorithms, we may be able to find the trends, and therefore we may be able to find the solutions that we are looking for. Yes.
Yeah.
So
okay. So we have more questions. There are more questions coming up. So, one from Mr. Satish Kakkula. He is head of South Asian Polo Center of Sustainability, joining from Bangalore, India. His question is, how would and what extent it is advisable to use nuclear energy in place of fossil fuel energy?
The question here, I mean, I'm not somebody who is for nuclear energy or against nuclear energy. What I see it is that it is one way of generating power that does not impact the environment in the same way as the fossil fuel does, but it has a safety and security problem. If we can satisfy the safety and security problem, then we should go for it. If we cannot satisfy the safety and security problem, it is infeasible, in my opinion, because it can give us energy that we need, but it can, with one accident, kill everybody. So if we can satisfy the safety issue, this is a very good option. And not one kind of technology is going to solve our problem. We need to have a combination of all.
Okay. Okay, sir.
And we see that also that the resources are not uniformly distributed. So where solar power is there, solar energy is there, we should use that. In some places where no other alternative is there, if the safety concern is satisfied, we use it.
Okay, we have more questions. Muhammad Tahmid, he's from one of our graduate students here, Muhammad Tahmid. He's asking that, I read once that all the agricultural land in the USA is not enough to produce biofuels to satisfy the energy requirement in the transportation sector alone. Other renewable sources like solar or wind also have large land footprints. What is your take on this? How practical is renewable energy in densely populated countries like Bangladesh?
Well, first thing I would say is that I would never even suggest that we should use our valuable biomass to make fuel so that people can have 2 cars or 3 cars instead of 1. That's what people would do in USA. I mean, why should I spend all my efforts to make this biofuel to see that somebody else is just misusing that? So I don't think we should use biomass for biofuels at all. We should use it for chemicals. At the same time, and that's also one could say that if one calculated how much bioethanol would be needed for USA only, for US consumption only, we need 3 times the size of Earth.
Okay.
To produce the biomass.
Okay.
So these kind of things people don't look at. And biomass should be used, bioprocesses should be used to make chemicals. For example, polylactic acid. That can make plastic alternatives that will solve the problem that we have now. Okay. But it's not cheap now. So if we can make it cheaper, that is where we should go. We should not use the biomass for transportation fuel.
Okay. Okay, sir. We have more questions. One question is from Professor Chinmay Goroi. He is from IIT Gandhinagar. He is the Associate Dean there. He said, great session of Professor Gani. Thanks to Buet for arranging this nice presentation. Professor Gani talks about preventing over curing in slide 18. And indeed it is true, but very hard to convince industry and sometimes policymaker. While the curing is more of engineering of existing processes like process intensification, selecting the proper processing routes is the best prevention route. But how to put a restriction on a new upcoming industries that unless they do all the optimization related to energy, water, safety, etc., we are not allowing them to set up their industry. I agree with Professor Gani, we need to influence policymakers too on this direction. Need chemical engineering community, irrespective of the geographical location, to work together to share and promote global best practice, including safety. Actually, he has comments. There is no question, but yeah, anything?
And I agree with the comments. The only thing I would just add is that yes, when we are designing a process, I mean, these days, there are the sustainability measures, they need to be improved also. But if somebody designs a new process, they can show all the impacts studies that they have done and that there are no other alternative better than this. And then if that alternative is going to have some problems, what are the future probability of having these problems? So again, data analytics would be very useful to predict that. We have looked at all these are done, but in the future, we don't know how the prices will move or how the raw material availability will change. But if it does, this would be the scenario.
Okay.
And can our design take care of that?
Okay, sir. We have another question from Hasim Hasnat. He is from Unilever, Bangladesh. His question is how chemical engineers can contribute in waste management in Bangladesh, especially for plastic, to make it linear or circular, linear to circular, maybe entrepreneurship initiative from chemical engineers, which will help Bangladesh for future. Any comments, sir?
Well, plastic is a big problem, and first is to collect the waste because it's polluting everything. So one thing is to collect it. We have to reduce the use of it by finding alternatives. And then we also have to see what we can do with it. And here again comes the question of linear or circular. It will not be linear. Well, linear is not a solution, and it cannot ever be circular because of the thermodynamics. But we could say that, yes, we will collect this plastic, we will reuse it for something else. And the question is, how many times are we going to be able to recycle it? Every time we recycle, we are going to lose some. That's the thermodynamics. Entropy has to increase. So ultimately, after fifth recycle, we won't have anything more to recycle.
Yeah.
But we do need to find out how to recycle the plastic. And what I've seen is that they make something else and then make something else. So as another example, I've seen that as example of circular economy, which was not circular, they showed that all the clothes, jeans and other things that people throw away, they collected those and they made a carpet. which looked very good. But my question to them was, okay, now you have made the carpet, but what do you make after the carpet? And what do you make after it? Because every time you're losing material, and ultimately there won't be another recycle to do. So from an engineering point of view, it is a sustainable circular economy, and we have to delay the circle going to the center as much as possible. And before it happens, we have to find another technology. Only that way, which actually becomes the same as sustainability. So it is just another term which is the same as in sustainability, as far as I'm concerned. But you can get more research money by talking about circular economy.
Okay, so we have questions from Professor Shaukat Chaudhary, who is basically coordinator of this Naser Chair program for this term. He asks, during this pandemic, use of fossil fuels has been reduced significantly. How is it contributing to reduce GHG emissions? Is there any research for calculation on it? How much temperature is lowered?
Well, I think immediate measurement, immediate analysis is not possible, but I'm sure people are measuring, and there are centers that have already reported that the quality of air has improved. In cities like Beijing and Delhi, in Mexico City, the smog has disappeared. So these are positive developments. In addition to, of course, people dying, but the air has become cleaner for sure. I was told that from some places in India, you can see the Himalayas now.
Yeah. Okay, sir, we have more questions.
Can I ask one?
Yes, sir.
Sure.
Sir.
Yeah. Well, thank you, Rafiqul Gani, for a wonderful presentation. First, this 2 degrees centigrade. In fact, there was some beautiful articles in the Washington Post. Already some parts of the world, the temperature has increased to more than 2 degrees. Even in some places like Japan, some isolated parts of Korea, and Qatar is one of the places where it is above 3 degrees centigrade. So time is very important. Your input-output model looks like a steady-state solution you're looking for. But it looks like that unsteady state solution we need to pay attention, because time is a critical factor.
Yes.
So,
Well, actually, I would say that the analysis is not just steady state. It depends on the problem.
Okay.
It can be steady state, it can be dynamic.
And
it depends on what you're monitoring.
Okay.
One other thing I would say is that actually the temperature increase is actually the global average temperature increase, not location temperature increase. Because
global is still under 2, yes.
Yes, so global is still under 2. And also, I mean, according to the data, the average Earth temperature now, 2019, is 14.3. That doesn't mean that 14.3 centigrade is all over the world. Some places is below, some places is above. But the average at this moment is 14.3. And the data that they're giving, they're actually collecting the dynamic data, and then they average over 5 years. And then they give these average values.
Yeah, the other point is about the input. The energy input is one of the most important factors. And I think there it has to be probably solar energy. And in terms of solar energy, You know, I was not aware that actually in 75 minutes, the amount of solar energy that you get covers the yearly total requirement. So it is the question of technology. Can we harness it? So
I think there is a lot of research going on in solar energy. I know a good friend of mine who lives in Holland. He and his friends in that area have all converted to solar, but they're connected to a power grid. And the way it works is that the power grid with the computer and everything figures out how much each house needs. And if the solar energy is not enough, they will give the fossil energy. If the solar energy is enough, they will have the solar energy. And if they're producing more solar energy than they need, that will go to the grid.
Yeah.
And then what they found out was that initially they had to invest, but now actually they're making money. So the technology is improving, and a lot of improvement is necessary. And this is the free energy. So if we can find, but the problem again would be material.
Yeah, and there is so much of solar energy, which is something. In 75 minutes, you get the total energy requirement of the whole Earth per year. So,
but again, I mean, if 1 billion people use solar energy, will the material that is needed for solar energy?
And then question of material will come.
Yes. So that is a big issue. So supply chain is a big problem.
Okay.
The last point I want to make is about nuclear energy. Is nuclear energy for a country like Bangladesh? No, because it is so much of high density population, and there will be accident, you know, small or big. And for a country like Bangladesh, we just cannot have nuclear energy.
I'm not promoting that. I'm just saying that.
Yeah, I know you are not.
Option. Bangladesh doesn't need to use it, but countries like France or USA or Canada, they're using it.
Yeah, they're using it. That's fine.
So it's a distributed system that is needed.
Thank you, sir. Thank you, sir. It was a nice discussion. We would love to hear more, but we have few more questions. And yeah, I mean, from Mohammed Jahidul Haq, he says, if he's from CAFCO, he says that is carbon dioxide capturing technology from boiler reformer feasible in economic context in our country?
Capture technology is very, very good these days. I mean, whenever I receive papers, they say they can capture 99%, no problem at all. And I tell them, tell me what you will do with this capture CO2. I mean, where are you going to store it, or what are you going to do with this captured? There are hundreds of different ways to capture the CO2. But if we cannot use it or do not know what to do with it, what's the point of capturing it?
Okay, another question. It's a bit detailed. From Ashfaq Iftekhar said, if we know the design targets or product specification, can we use machine learning to train our model to come up with the required input material to produce such project as means of inverse design? For example, if we know our desired permeability, can we not come up with a membrane material that has the desired permeability?
Yes, but for the machine learning also needs data. Is there enough data?
Okay.
If there is enough data, then, because machine learning also is that we have to teach the system what to look for. And if we cannot teach the system what to look for, it's not going to look for it. So yes, it is possible, but and there is actually work going on that. Even we are doing it. together with Farooq Hassan and his data, that can we find an adsorbing material that will selectively capture one gas and not the other.
Okay. I think one of the last questions we have here, it's from, just a second. It's from Sheikh Yasir Arafat Siddiqui. He's from Joshua University. Like he's one of our faculty members in one of the universities here. It could be Joshua University of Technology, if I'm not wrong. He said that, sir, I have one question regarding the power sector plan of Bangladesh. Several large capacity coal-based power plants are under construction, and also few more contracts or MUs have been signed. In fact, the fuel mix for future power production will heavily rely on coal. Presently, it is on natural gas, as per PDB report. What is your suggestion regarding this? Which sources should be prioritized for future power production? What is our role? What our role could be in this sector?
Well, I would say that maybe the wrong people have the wrong influence on the decision makers, because it depends on who is able to give the influence the decision makers. This was certainly, I would say, wrong influence, because from an environmental point of view, nobody wants to touch coal. If Trump is no longer president, coal will be stopped immediately. China is reducing the amount of coal. We need to do more research to find out better ways to use coal and then use it even for power plant. But coal can also be used as raw material for making new chemicals. But if the plant is already built, it's already built. And then I would say that maybe together with the power plant, the capture of CO2 should be installed, and then one has to find out what to do with the CO2.
Okay. Okay, sir. We are, yeah, I think we are almost at the end of our program. At this point, I do not see any more questions. At this point, I would like to invite Professor Ijaz Hussain, Dean of Faculty of Engineering, BUET, to say a few words for us. Professor Ijaz Hussain.
Thank you, Professor Razia. Can everyone hear me?
Yes, sir.
Okay, good. Because with these days, you're not sure whether your system is working or not. And I was very pleased to find that Professor Gani's system was working extremely well, and I just kept it on, and it was a very pleasure to listen to him. A wonderful talk he's given, and as usual, very informative and very, very enjoyable. And I'm particularly happy that this program of ours, where we have the Professor Naser chair, has been very successful. I mean, we've had very, very good previous Naser chair holders, scholars, and the present Professor Rafiqul Gani is particularly very, very sort of good for us in terms of getting the BUET Chemical Engineering Department recognized throughout the world. What I noticed that there were 67 people who had attended. I don't know how many people there now, but this is very good. I mean, had we organized this here, we probably wouldn't have had that many people. So despite the fact that the COVID has put us into a very difficult situation, the human ingenuity has given us ways to sort of maximize the benefits of having Professor Rafiqul Gani give us a talk on sustainability. The questions were very, very good, and as you know, energy is my area, and I've worked in energy all my life, including climate change mitigation and things like that. And I've actually worked very much on the ground with energy, the reality, the real field, and often I find that the people who talk about solar energy, renewable energy, and whether coal and this, somehow a lot of the people are kind of off track. With renewable energy, I just like to point out, we have a problem that when the sun shines, you've got electricity. When the wind blows, you have electricity. Okay, like these are two major sort of renewable energy that we have. Biomass, as you've discounted, it can contribute a little bit. Then there's geothermal and all. So to get total energy from renewable sources, we are extremely dependent on batteries. Okay, and I fully appreciate the thing that Professor Gani you mentioned, that whenever you look at it, those kind of things, and you run into the thing about materials. Okay, and do we really have that amount of batteries in the world to store all the renewable energy right now and give it to everybody? We don't know. So I think this argument about how much renewable and how much fossil fuel is really unproductive. It's like, what do we need now? Let's go for it, and that's exactly happening. Renewable energy is doing very, very well. It's coming in the forefront and doing its job. But there are areas which is can't. So we don't know really which one will win or how much of it will be there in 2050. So that's the reality. The reality is that we don't know. The other thing is that with this thing of coronavirus and COVID thing, we've been really thrown into what is called the new normal. And the new normal has really shown that how unsustainable our lifestyle is. And despite all the technology and all the things, we are simply lost. The medical world and the sort of the combined sort of efforts of the whole world cannot really control a virus which is really part of human existence, of life, and we don't even know. There are people who talk about herd immunity, and then a lot of people sort of discredit them, and then whether we should wear a mask, and everything put together really has shown the extreme limitations of our knowledge in certain areas. So this kind of work that Professor Rafiqul Gani is doing is extremely important, and really, right now we have about 7 billion people. Is going to increase, and if everybody is going to survive and we want to improve life on Earth, we have to find better and better ways of doing things in the new normal. I don't want to sort of elongate my talk. I'm very, very happy that so many people attended this webinar, as it's called, and Professor Rafiqul Gani gave us an extremely good sort of presentation and look into the future. I like to just mention one thing, that in slide 29, you mentioned this very famous sustainability expert who was given a slide, and I noticed that it's in 2013, and in 2013 in that slide there was one health component and in the sustainability side, and to think that that he actually thought about that in this sustainability loop, as engineers and other people, we've never really included health as it came in along with environment and all, but directly taking health, aspects of health and improving health and how to deal with this kind of issues into the sustainability sort of matrix wasn't there, and so he is really sort of way ahead of a lot of people in bringing that thing. And then from now on, we'll just have to sort of keep that in mind, that the new normal will include health. It's certainly with health. I like to point out, as a chemical engineer, and I find this mask thing extremely sort of troubling and disturbing, whether you should wear mask or not. As a chemical engineer, I like to narrate this experience when I went to visit a chemical plant. We've used masks forever. We are really the experts of masks. I went to visit a plant in Canada, and they won't let me in because I had a beard. I said, why? which is, look, it's useless. I mean, your mask can't seal with a beard. So right now, people are putting this mask, and you know, what are they doing? And they are putting 2-3 masks, one on top of another, and they're forgetting that if you increase the resistance on the top, the air is going to go in from the side and all over the place, and really frustrate the mask. So really, I mean, you see that the knowledge, really the scientific knowledge and the common knowledge and everything has just gotten mixed together. Anyways, I don't want to elongate my sort of speech any further. I'd like to thank Professor Rafiqul Gani for giving this talk and taking the time, making time for this. And I'd like to thank everybody else to be part of it. And I think that if all of us sort of unmute our mics and show him some appreciation, that would be wonderful. So, you know, can we all unmute our mic and Professor Gani, if you want to say something, last few words.
Well, first of all, again, I would like to thank the department for organizing it. Professor Razia, Professor Shaukat Chaudhary, Dr. Sanjida, and of course, you and all others. I would also like to thank my teachers when I was studying, Professor Iqbal Mahmood sir, Professor Joshima Zaman sir, Khalikur Rahman sir. I think I hope I've not missed anybody else, but these three I could see have registered there. So thank you very much for attending it. I hope I've given a view that you could agree with or disagree with, but at least you can think about it. It was a great experience to prepare for it. That's all. Thank you very much.
Okay. Thank you, sir.
And stay safe.
We're going to get the presentation, right?
Yes, sir.
Yes, you can freely distribute. I've given a copy to Sanjida.
Yeah, so I just want to close this program by saying that we had participants from Bangladesh, Australia, India, UK, and US. And also we are at the end of our program, and on this occasion, we gratefully recall the initiatives and sincere efforts of our senior alumni and Chemical Engineering Alumni Association as a whole towards establishing the Naser chair. And we are congratulating Professor Gani for this wonderful webinar. We thank our participants for joining us today and for making this webinar successful. And I also thank Professor Shaukat Chaudhary and Dr. Nahi Sanjida for coordinating and co-hosting this webinar and for their efforts to make this program successful. We pray for all of your health and safety at this unprecedented time. Thank you very much once again for joining us.